Silicones are used extensively in electronic devices at component, board, and device assembly levels. Silicone materials provide protection from heat, electromagnetic interference, as well as many mechanical and environmental stressors that impact performance and reliability. One of the primary reasons to choose a silicone for these applications is their remarkable durability over a wider range of temperatures and other environmental conditions than other protective materials. Extreme durability often comes at a penalty of reworkability. Epoxies, for instance, are often cited for their great strength and adhesion, but once electronic modules are assembled or encapsulated with epoxies, they are nearly impossible to repair or rework. The inability to repair or rework parts leads to much higher scrap rates, cost, and environmental impact. Silicones impart high reliability in many devices, and yet often allow for easy repair and rework across all levels of electronic applications. Silicones are typically soft to very soft materials that can be tough, yet relatively easy to cut and mechanically remove. There are several common methods to remove silicone, which can be used singly or combined for greater effectiveness. These include mechanical removal, chemical or solvent removal, micro-abrasive removal, and de-soldering through a conformal coating. Let's go through each of these in more detail. Silicone thermal greases can be easily wiped off, but all other products cure into rubbery materials of varying hardness. As mentioned, cured silicones can be tough and impact resistant, but they generally are easy to cut, tear, and abrade. To begin mechanical removal, start with bulk pieces that can be cut and removed. Take care not to damage underlying or adjacent surfaces and materials. Cutting a V shape into the silicone is effective to begin tearing out the bulk silicone pieces. Work through thicker gels and encapsulants in layers to reach down to the board level. Solvent can be used to assist with weakening the cured silicone and can be injected into the V groove. Solvents swell silicones without causing lasting degradation or damage, and once the solvent has evaporated away, the remaining silicone should return to its original dimensions and properties. Solvent-swelled silicones can be easier to remove from surfaces. While very few chemicals will dissolve silicones, many solvents will cause silicones to temporarily swell, which greatly aids mechanical removal. Silicones have the largest swell in nonpolar solvents such as toluene, xylene, mineral spirits, naphtha, hexane, heptane, and other solvents typically used in degreasing operations. Dowsil OS fluids work exceptionally well. Alcohols, such as isopropyl alcohol, and ketones, such as methylethyl ketone and methylisobutyl ketone, cause less swelling, while water-based solvents will cause little to no swelling and are therefore ineffective to help with removal. Dow offers two chemical strippers useful to remove cured silicones. Dowsil DS-1000 aqueous silicone cleaner has been used to soften and weaken cured silicone to aid in their removal. Dowsil DS-2025 silicone cleaning solvent is designed to depolymerize and dissolve cured silicones. These chemical cleaners should have minimal impact on non-silicone materials, but thorough testing should be performed to verify they cause no performance issues on electronic devices. Carefully read all supporting literature and instructions for these products before use. Highly filled conductive silicones will have the smallest swell in solvents. Silicone gels, coatings, and soft rubbers will swell much faster and to a greater extent than harder silicones. All of these silicone products started at the same size before swelling with OS-20. Similar to solvent swelling, silicone chemical strippers are most effective with gels, coatings, and soft elastomers, and least effective with highly filled conductive silicones. If certain areas need to be unaffected in the rework process, parts should be coated with solvent in small doses. Silicones tend to swell within just a few minutes of solvent exposure, and since the solvents tend to migrate into adjacent areas, the repair work should be done promptly after exposure. Only apply enough solvent to achieve the rework to avoid excessive swelling of surrounding areas. If using a fast evaporating solvent, reapply sparingly as needed. Another item to address is the expansion pressure created as silicones swell with solvent. Solvent swelling of a silicone can create pressures of a similar magnitude as that caused by thermal expansion. Silicone expansion under sensitive components and wire bonds can create damaging stress, so care should be exercised to minimize solvent swelling in undesired areas. Swollen silicones can be easily removed with gentle scraping or light abrasion. Special thoroughness may be required in rework locations where repair work like soldering is needed. The next method of silicone removal in this discussion is microabrasion. Microabrasion removal uses high-velocity particles directed through a nozzle to etch away a silicone coating. Common abrasive media includes ground walnut shells, glass, or plastic beads and sodium bicarbonate powder. This technique can be used after deeper sections of silicone have been removed by previous methods to more thoroughly remove silicone residues that may interfere with repair soldering, and sometimes as the entire removal process for conformal coatings. Avoid embedding abrasive media into silicone adjacent to the repair area. This can be aided by masking with aluminum foil or plastic wrap. Static charge can be generated with this method as the high-velocity particles travel through the lines. Many systems have anti-static ionizers and grounding points contained within the unit. Static discharge can damage sensitive electronics that were otherwise protected by the removed silicone. The last silicone removal technique that will be discussed is de-soldering. De-soldering can sometimes be used to burn through a silicone conformal coating to remove electrical components without having to first remove the silicone. Resoldering can also be done with minimal further cleaning. Directly adjacent silicone to the solder points may become harder and whiten from the heat. This white silicone can be mechanically removed prior to reapplying silicone over the repair area. After rework is completed, silicone can be reapplied to the surface. Some preparation is required to ensure the silicone will cure and adhere to the surface. For soldered circuit boards, all residual flux should be removed with solvent. Also, solvents used in cleaning should all be evaporated before application of additional silicone layers. The evaporation process can be accelerated by drying out the part in an oven at low heat. Once all silicone areas appear to have returned to normal dimensions, a final higher temperature exposure can be used to further reduce any residual solvent that might remain. When using a chemical stripper, special care must be taken to thoroughly rinse and remove all traces to ensure it does not interfere with or dissolve newly applied silicone. Repairs can often be completed just by applying more of the original silicone product over the removed area. Repaired surfaces should be clean and free from debris. While silicone gels typically bond well to themselves, other addition cure silicones generally do not form strong bonding when applied over other silicones, even when a given product is applied over cured sections of the same product. If stronger bonding is required, 1-part moisture cure silicones are typically used to cover and fill the repair areas. Using a Dow-Sil primer on bare surfaces can enhance adhesion, though this technique usually does not improve adhesion to cured silicone surfaces. Overlapping the surrounding original silicone can often provide enhanced device protection. While devices coated, encapsulated, sealed, or bonded with most dispensed and cured materials are difficult to impossible to repair or rework, the use of silicones typically allows these operations to be performed easily. Silicones cut easily to allow for simple removal, and solvents or chemical strippers will swell, soften, and weaken cured silicones for easier mechanical removal. After a thorough cleanup, silicone can be applied to replace the removed material to return the device to proper functionality.